So crystalline solids, they are different because they have a lot of order in the way that they are arranged at the atomic / molecular level. So whenever these are cooled slowly, the particles within them, within this liquid specifically, will arrange so that they have the maximum amount of attractive forces between them. Overall, this minimizes the energy, and what you end up getting is crystalline solid. So the arrangement that these particles take is called the lattice, the crystal lattice. So you can see here how it's kind of like a system, and it basically looks like a bunch of cubes, you know, stacked on top of each other. And that's what a crystal lattice is. If we imagine like the corners being certain atoms or particles. The smallest unit of this, you know, network pattern of little cubes is called a unit cell. So one individual little cube is called a unit cell. Before we move on to learning about the different types of lattice structures, we need to describe some certain terms. So lattice point, for example, is each particle in the unit cell. So here you can see that at these corners, they will typically be particles, right? So each particle is a lattice point. So it's a corner of that lattice unit cell. Lattice planes are the planes connecting equivalence points in unit cells throughout the lattice. So all these are the sides of the lattice unit cell that connect the unit cells to each other. Coordination number is the number of particles each particle is in contact with. So for example, if we are looking at one central particle within, how many? These are 8 unit cells all connecting together. If we looked at the number of particles in contact with this one that we are looking at, this red one, we would see that there is a total of 6. So the 4 around it equal like equatorially, and then axial, so above and below, there's 2 more. So total of 6. So the higher the coordination number, the more interaction and the stronger attractive forces that hold the crystal together. The packing efficiency is the percentage of volume in the unit cell occupied by particles. So the higher the coordination number, the more efficiently the particles are packed together. So there are 3 types of unit cells we're going to talk about. They are all cubic. The first of the 3 is a simple cubic unit cell. So all of these unit cells we can think of as little cubes, which have a length, width, and height that are all equal to each other. The angles between the corners are all 90 degrees, so typical cube. Now, the major things to know about these simple cubic unit cell are right here. So first of all, there are 8 particles, 1 at each corner of the cube. So you can see here that there's a total of 8. We have 1, 2, 3, 4, 5, 6, 7, and 8 total. Now, only 1/8 of each of them is actually within the unit cell. So you can see how the outline of the unit cell is kind of inside, and that is because when we're looking at each unit cell, not the entire atom is actually within it. So only 1/8 of each of them. Now, because there are 8 atoms per that unit cell, so 1/8 times 8 of them, that gives us a total of 1 atom per unit cell. Now, it's not like a cube like this and then, sorry, horrible drawing skills. It's not like you just have an atom within there, right? It's that you have 1/8 of 8 of them total, that adds up to 1. The edge of the unit cell is twice the radius. So if we were to look at this from the top, so let me just draw an ugly drawing again, we would see that we have something like that, right? So that's half of the diameter of each atom on those 2 corners. So because of that, the length of this cube will be 2r. So that's how you would get the edge of that unit cell. And then finally, the coordination number would be 6. So remember we talked about coordination number, how it refers to if we were looking at one particular atom in the center, how many atoms are around it. So in this case it would be 1, 2, 3, 4, 5, 6. So in this example, we will be calculating the atomic radius and also the density for a metal. And this is for a metal that arranges in a simple cubic cell. So this is alpha polonium, and they tell us that the edge length of this unit cell is 336 picometers. And of course they tell us it's a simple cubic unit cell. So we know this is how the unit cell looks. And this is what I was trying to explain earlier, how the edge length is equal to 2r, right? Half of a radius of each of those atoms, each of those 1/8 atoms at the corners. So first we're going to determine the radius, and then we're going to determine the density. So the first part is actually pretty simple. The second part is the one that will require like you paying attention to this problem and taking some notes, and then from there you will be able to do some more problems on your own. Not because I don't think you can, but because this is going to require again some refreshing on dimensional analysis. So just watch this video and it'll definitely help you. So for the first part, A, we are determining the radius. Now, like we said, the length is equal to 2r, and because they actually gave us the edge length right here, 336, we know that this is what it's equal to, and that each radius, that we can calculate the radius basically from this. All we have to do is divide both sides by 2, so we're just doing some algebra, and then we get the radius, which is equal to 336 picometers divided by 2, which is equal to 168 picometers. So that was pretty easy. We got the radius. So the radius is 168 picometers. Now, in order for us to get the density, there are two things that make up a density. So there is, and this is again review, mass divided by volume. We need mass and volume. So one thing that we can get for sure, pretty simple and easily, and I think it's easy like to conceptualize, is for the volume of a cube, all we have to do is multiply the length times the width times the height, right? You guys remember that, hopefully, from like high school algebra maybe. Yeah, that's all we have to do. And because we have the length, right, we have the length as 336, all we have to do is multiply that, cube it. That's all we have to do. Multiply it by itself 3 times. Now, usually for densities, the volume, well, the mass will be in grams, and then the volume will be in ml or centimeters cubed. In this case, because it's a length, we are going to want this to be in centimeters. So we're going to convert that 336 picometers to centimeters first. So this is some dimensional analysis. So if you want, you can convert to to meters first. So 1 picometer is equal to 1 times 10 to the negative 12 meters. Now from we can convert to centimeters. So we are going to want meters at the bottom. So 1 times 10 to the negative 2 meters is equal to 1 centimeter. And from there you just plug it into your calculator and you should get your value. And we end up getting 336 times 10 to the negative 10th centimeters. So now that we have that, we can go ahead and work on cubing it to get the volume. So I'm going to take this up here. So 336 times 10 to the negative 10th. Sorry for the handwriting. All you have to do is type it into your calculator, put parentheses around it, and then cube it. From here, you should get the volume being equal to 3.79 times 10 to negative 23rd centimeters cubed, right? So now we have the volume. We have this unknown so far, our volume, but now we need the mass. How do we get the mass? So this one's a little bit trickier. So you're going to have to do some dimensional analysis, and then we are also going to have to use some knowledge that we know about simple cubic unit cell. So we know that in one simple cubic unit cell, so I'm going to abbreviate, in one simple cubic unit cell we have a total of 1 atom. So in this case, in one polonium unit cell, we have 1 polonium atom. So this is our major conversion factor that will get us to eventually mass, right? So we're searching for mass. That's our unknown right now. We know that we're actually starting off with 1 polonium unit cell. This is our starting point. And like I said, if this isn't coming to you like conceptually, it's okay. That's why you have this example here. Next, we are going to convert to atoms of polonium. So in 1 polonium unit cell, and this is using our conversion factor that we just determined from information that we know about simple cubic unit cells. So in one of these, we have 1 polonium atom. Eventually, we want to get to grams of polonium, right? So if we're starting off at atoms, we can actually use our mole map, and we're starting off at atoms on this side. So next we would use Avogadro's numbers. Let's go ahead and set that up. So at the bottom, we are going to put atoms. Polonium atoms. And then at the top, it'll be 1 mole of polonium. Now that we're at moles, this is a very good state. And all we have to do left is to convert to mass. And to do that, we are going to use polonium's molar mass. Sorry, this got kind of messy, but 1 mole of polonium. And this mass, I'm just getting it from the periodic table. So you just look at the periodic table, whatever mass it has, it's grams. You'll have that number, and then grams, and then divided by 1 mole. So for polonium, it's 208.998 grams. Like I said, sorry about the messiness. Now, from here, you should get grams, and when I cancel everything out, we do see that everything cancels out, which is good. And all we would actually have to do is divide 208.998 divided by 6.022 times 10 to the 23rd, and we end up getting 3.47 times 10 to the negative 22 grams. Now, last part, we're about to finish. We will take this mass that we got to get density, 3.47 times 10 to negative 22 grams, divided by our volume, which is right here. So I have the main 2 things that we need right here circled. 3.79 times 10 to negative 23rd centimeters cubed. From here, we divide these out using our calculator, and you should get 9.16 grams over centimeters cubed. So this is our density. I know this is a lengthy problem, so that's why you break it down step by step. First, we found that volume, which was the easier step out of the 2, and then finding the mass was a little bit, I mean, it's not necessarily tricky. We're just going from unit cell to atoms to moles and then to grams. It's just having this example for you will definitely help you. So use it, take notes, and then you can be able to practice one of these types of problems on your own. Next, we have our body-centered cubic unit cell. So like I said, we have 3 of these total cubic unit cells. This one we learned about simple, and now we're going to learn about body-centered, so BCC. So for this one, it's different in the sense that instead of just having those four outer particles or atoms on each corner, you actually, and on top and bottom, right, you actually have those 8 total and also 1 in the center. So you can see that atom right there in the center. So total, you have 9 particles in this unit cell. Now, how much of each particle, how many total atoms do we have being composed of these different corners? So we have those 8 corners times that 1/8 that each of them have in the unit cell. So total, that's 1 atom right there, plus the 1 in the center. So total, we have 2 atoms in this unit cell, okay? So in the body-centered cubic unit cell, we have 2 atoms. The edge of the unit cell can be calculated using this times the radius of the particle, and then the coordination number is 8. So instead of 6 for this one, it's 8. Finally, we have the face-centered cubic unit cell. So as hopefully you've noticed, these are kind of getting more complicated, and that's because, you know, we start off with the simple, it just has those 8 corners. The body-centered has 1 in the center plus those 8 corners, and then this one has actually 14. So 1 at each corner, just as we've been talking about, and then 1 in the center of each face. So there are 6 total faces on a cube, right? That makes sense. So there's a half an atom at each of these 6 faces, and then 1/8 of an atom at each corner, so total 8 corners. When you multiply all this out, we end up getting a total of 4 atoms. So you have that half times 6, and then that 1/8 times 8, that ends up equaling 4. So in this case, we have a total of 4 atoms per face-centered cubic unit cell. And then to calculate the edge of the unit cell, it would be 2 times square root of 2 times the radius of each particle. And here the coordination number is even higher. So that means that we're packing even more particles per unit cell. So the coordination number is 12. So something interesting about the face-centered cubic is that it's actually considered cubic closest packing. So in cubic closest packing, you have 3 repeating layers of hexagonally arranged atoms. So you can see here these 3 layers, so the green, the blue, and the red. Now if you turn it over and arrange it the way that a face-centered cubic cell is arranged, you are able to see the 3 different layers. And here I have the regular face-centered cubic just to for you to be able to compare, and you can see that they're arranged in the same way. So each atom contacts 6 atoms in its own layer, and then 3 in the layer above, 3 in the layer below. So in this arrangement, each atom will touch a total of 12 neighbors, and that's why it has that coordination number of 12. We also have something called hexagonal closest packing to describe other different packing types. So in this type, it would just be 2 different types of layers. So for cubic closest packed, it's 3, right? Different layers, A, B, C. For hexagonal, you just have A and B. And the way that they sit on each other is that the second layer of atoms will sit directly over the atoms in the first layer, called the AA pattern, or the second layer can sit over the holes in the first layer, called an AB pattern. So there's 2 different types. So now we're going to calculate the radius and density for a metal of a face-centered cubic structure. So this one's a little bit more complicated in terms of finding the radius, but the other part, finding the mass, is actually the same type of process, and so is finding the volume. So once we get that radius, we'll be good to go. We can use the previous example as our template. So I'm going to go a little bit faster on this one just because we've already been through the basics of this on the previous problem. So finding the radius, like I said, is the more difficult part of this problem in particular, and this is because we are looking at 3 different radius using that diagonal cross section of the cube. Now the reason for this is because we have a different arrangement. It's not the same as the previous one where we just have 2 radius and we can figure out we can have the edge length and figure out the radius from there. So in this case, we're going to have to do some math, and this is the Pythagorean theorem coming back to haunt you. It's okay, it's simple, but all we're going to do is find our C, we have our A and our B, and we're going to solve for that C. That's all we're doing. So we know that our A and our B are both equal to 558.8 picometers because the problem tells us right here that the edge length is 558. So both of these are 558.8 picometers. So what we have to do is find that and then square root it. So keep in mind that our C is equal to 4r. So this is how we're going to set it up. We have our A squared plus B squared equals 4r squared. So I'm going to fill in 558, 558, and then we'll start from there. So this is what we have so far. We have our A squared and our B squared equal to our 4r squared. So we're trying to solve for that r. So we are going to try to isolate it, and the way we're going to isolate it is we are first going to square this 4 right here. That gives us 16, right? But the r is still squared, so whenever we distribute this out, that's what you'll get. You'll get 16, but you still have that r squared because it applies to both. Now, in order to take away this 16, we're going to divide both sides by 16, and then we end up having this entire side, right? The 558 squared plus 558.8 squared divided by 16 equals r squared. So I know this might be going fast, so just pause the video if you need to like catch up on the notes. So from here, we will square root both sides. So I'm going to write it in a different color. So I'm square rooting and I'm square rooting. That square root takes away that squared on that r, so we end up getting r, and then all of this right here that I just circled. This is what r equals. So once you plug that in, and make sure to put all the parentheses around it in your calculator, once you plug that in, you should end up getting 197.6 picometers for this calcium radius. And I forgot to point out, but it's calcium. So like I said, this was the most difficult part of the problem, using that Pythagorean theorem to find our 4r and then solve for r by itself, the radius. Now, next should be a little bit easier. So we are going to find the density. To find the density, we need the mass and the volume. Remember that the volume, I'm going to circle this off, volume is just equal to the edge length cubed. So this will be equal to our edge length in picometers. We need to convert that to centimeters, and once you convert it, I'm going to let you do that on your own, but you should get this right here, 558. And I mean let you do it on your own because we did it earlier, so hopefully you can do that. If not, just let me know, I'll help you. And then we're going to cube that. So we cube that, and you should end up getting, for your volume, 1.745 times 10 to the negative 22 centimeters cubed. So we have our volume, check, right? But we still need our mass. And again, we are going to set up that dimensional analysis for this. So for the mass, we need to know this information. We need to know that in one face-centered cubic cell, we have 4 atoms. Regardless of what type, as long as it's in this type of cubic unit cell, you will have 4 atoms. So in this case, in one calcium unit cell, sorry for the horrible handwriting, we have 4 calcium atoms. So this right here is our conversion factor. So we're starting off with one calcium unit cell. we're going to use that conversion factor we just talked about. 1 calcium unit cell means you have 4 calcium atoms. From there, we will use the mole map. So we're starting off with atoms. We're going to use Avogadro's number to get to moles. So 6.022 times 10 to the 23rd atoms of calcium is 1 mole of calcium. From there, we will, so we're here now, we will use the molar mass. So the molar mass of calcium is 40.078 grams calcium. So everything cancels out, double check it, make sure you have everything in the correct spot for this dimensional analysis. So for this, you should get 2.662 times 10 to the negative 22, these are some long numbers, grams of calcium. So now we have our volume and we have our mass. And now we can divide these two. So we are going to write out our mass divided by volume. And you should have the 2.662 times 10 to the negative 22 grams divided by that 1.745 times 10 to the negative 22 centimeters cubed. That's a mouthful. From this, when you divide this out, also, if I were you, just to make it easier to plug it in, I would notice that that times 10 to the 22, negative 22 cancels out. So you can just type in 2.662 divided by 1.745 into your calculator, and you should get 1.53 grams over centimeters cubed. So that is our density for this calcium face-centered cubic structure.